Yes, perfect.
Thank you very much. Yeah, so my name is Andrei Schwartz. I'm the postdoc at the University of Glasgow, also developing in the Morphem team. And my part of the presentation would be about the mixed finite elements, and in particular, we'll talk about function spaces, error indicators, and p-adaptivity. So the outline is the following. So I'll try to bring some motivation for using the mixed problems. And then before actually deriving the mixed weak form for a Poisson equation, we will need to discuss some preliminaries for the function spaces. Just recall what is L2, H1, Hdfinity Curl, and then we will discuss the implementation of the mixed weak form and the associated error indicators. And then using those, we will try to do some simple convergent analysis for a p-adaptive refinement algorithm. The PDF version of the slides is available also at the updated one is available at our website in the tab Getting Started School. And also there is a tutorial closely following this presentation also on the Morphem website titled Mix Zero. So it seems to me that one of the ways to introduce the mixed problem is to find its difference from the coupled problems. So coupled problems are usually the problems which are governed by different physics and therefore described by several variables, and then we look for interplay between those subproblems. And examples include thermal elasticity, electroelasticity, were classical problems, and then vast domain of fluid structure interaction problems, and more exotic things like magnetohydrodynamics and so on. Many others also exist. So in contrast to that, in the mixed problems, we consider one physical process, and then we ourselves introduce one or more additional auxiliary variables for the reasons that we will discuss in a minute. And there are a number of problems that permit such formulation, and also not just permit but benefit from it, like incompressible elasticity or incompressible flow. Then the problems of convection, reaction, diffusion, contact problems, and also many more. So the motivation for the using mixed formulation, there could be different reasons. Maybe the most important ones of them are the following. So the presence of constraint in the problem, such like incompressibility in incompressible elasticity or a flow, where we would introduce new variable for hydrostatic pressure, or contact problems where there's some constraints on the gap, and then we introduce the Lagrange multipliers, which are equivalent to contact pressure. Sometimes these new variables that we introduce are more important than the original ones. For example, in elasticity problems, we might be more interested to compute stresses accurately, or in diffusion problems to compute fluxes accurately. Furthermore, the mixed formulation provides a weaker formulation, and then it means that some problems we could benefit from less requirements on the regularity of the solution. And finally, last but not the least, is the fact that with the mixed formulation, it's very easy to implement and use error estimates, in particular a posteriori error estimates available after solution of the problem. So we'll concentrate about discussing those in this presentation, and it's important to differentiate between error indicators and error estimators. So error indicators are just local measures of the error, which could be useful to drive the adaptivity, while error estimators are mathematically strict bounds on the global error. We will consider for the only the first of those error indicators in this presentation. So we'll just need to recall some preliminaries of function spaces to fix the idea. So let's introduce the domain Rn, where in Rn where n can be 2 or 3. And then L2 is the Lebesgue space of scalar functions which are square integrable, and that gives also the L2 norm. And then the H1 is the Sobolev space for functions, also scalar functions from L2, whose derivatives are also square integrable, so that the derivatives belong to L2 space. And then we would look into two more spaces, which are quite different, as they are vectorial. So they're called Hdfinity Curl, and the functions in these spaces have components from where each of the components belongs to the L2 space. And Hdiff space is the space for such functions whose divergence is square integrable, so in L2, and the H-curl is the space where the curl is square integrable. And here is a small trick that in 3D, curl is a vector, but in 2D, there's a convention that the result of a curl operator is scalar. And I'll describe it in a minute because we will consider a 2D problem here. So with the diff operator, it's clear that the result is scalar, while for curl, in general, like in 3D, like I said, it is a vector. But if we consider only vectors u lying in the plane xy, then the result of the curl operator will always be perpendicular, and therefore it can be defined just by the scalar. And thanks to that, we could notice that we can compute curl of vector u lying in the plane xy as the minus divergence of a vector rotated by 90 degrees by a right angle. And that's quite important because from that comes that the spaces Hdiff and Hcurl in 2D are isomorphic. That means that if we have a base for one of them, we can easily construct the base for another by just rotating the base vectors by the right angle. We will use this later on in the implementation. And but in fact, the properties of these two spaces are quite different, and the main property of the Hdiff space is the normal components of Hdiff functions is continuous across any inner boundary in the domain, and that means that it's a natural space for flow problems, as we want the fluxes to be continuous for the conservation laws. And the classical examples of the finite elements which implement the Hdiff space are Ravier-Thomas elements. On the contrary, H-curl functions have the tangential components continuous across their inner boundary. And that means that such space is natural for the magnetic problems, where we want the magnetic field lines to be closed. And the example of the elements for this classical example is the Nedelec elements. So with these definitions, we can look into the Poisson problem. I will start first with briefly showing the same thing that Juan showed a bit earlier, just to show the comparison. So we start with the strong statement with the homogeneous boundary conditions, 0 on the boundary for the field U, where U can be temperature, for example, or concentration or electric potential, depending on the application. And then we multiply by test functions and integrate. And then integrate by parts, and we notice that since the Dirichlet boundary condition was embedded into the space of test functions, so it becomes essential, and the boundary integral vanishes, and therefore we end up with the standard weak formulation, where we're looking for functions in the space H1. So if we want to look into the mixed formulation, we would do what I was saying in the beginning. We would introduce the new variable for flux. So working with the mixed forms, we always start with introducing new variables. So here flux Q is the gradient of U, and then the conservation law is now formulated for the Q. Now we will, to make it weaker, we will integrate the first two equations by the test functions, and we notice that this second term over here can be integrated by parts. And now there's a small trick here, is that we could also drop this term over here, because as it vanishes, as we know that the U equals to 0 on the boundary. But here, in the standard formulation, the boundary term was dropped as a manifestation of the essential boundary condition. But here, U is not a test function. Delta Q is the test function. And therefore, the initial Dirichlet boundary condition acts here as natural. This is a typical trick for the mixed problems. And then we end up with the formal formulation. So now we are looking for the field, a vectorial field Q, from the space Hdiff, as there is the divergence operator acting on Q. And now there are no derivatives of the U. Therefore, we look for U in the space L2, such that satisfy the system. And as I was saying, there are error indicators naturally appearing in the mixed problems. And maybe the simplest one of them is considered here. The local error indicator is basically the norm of the difference between the gradient of U computed a posteriori after solving the system, a difference between this gradient of U and the computed flux. Or it can be integrated over the whole domain to give the global error indicator. So this is going to be the one we're going to use. And just to fix what we're going to look for, let's consider the example of the Poisson equation with the homogeneous boundary condition in a rectangular domain. And let's construct a problem for a given analytical function, which is 0 on the boundary and has some high gradients located in the center of the domain. And then we could analytically obtain the source term and therefore do the full convergence study. So I will try to go very briefly through implementation, as my colleagues already presented most of the parts of these tutorial programs, which are quite similar. I will only try to give more details about the specific issues for these type of problems. So, for example, there are some specific issues in the setup of the problem. Here, we would add two fields for the fluxes and for the field U. And for the field fluxes, we add we choose the space H curl. So this is not a mistake. Yes, the real space for Q is HDiff, but we use here H curl is because, like I was presenting in the beginning, the spaces H curl and HDiff are isomorphic, and therefore in 2D, and therefore for the 2D case in Morphem we implemented only H curl, and then the right space HDiff will be obtained after the rotation, which I will discuss in a minute. So we use the polynomial base from the Dymkovich-Jacobi polynomials, and I just want to remind that the HDiff, both HDiff and H curl spaces are vectorial, and therefore the base is vectorial. And to approximate the vectorial field Q, the flux, we would just need only one coefficient per each base function. For the field U, it's simpler. We just need to choose the space L2. And here we could consider a different polynomial base. This is one of the features of Morphem, that we can mix not only different spaces, but different polynomial bases to suit our needs. And here field U is scalar, and therefore we use only one coefficient per each scalar base function. And what's important is that with the mixed problems, we need to satisfy the inf subconditions. Here it manifests in the fact that if we use order P for the fluxes, we need to use the order by one smaller, so like P minus 1 for the field of U, which belongs to the field with less regularity, L2. So I want to give just a small overview of how these shape functions look like. So what's the hierarchical approximation basis for the HDiff and L2 fields? So for the P equal to 1, there are 4 HDiff vectorial base functions and only one L2 scalar function, which is in fact equal to 1 on the whole element. Yeah, in this example, we'll consider quad elements in 2D. So if we increase P, we consider P equal to 2, we get 8 more vectorial base functions for HDiff and 3 more scalar base functions for L2. And we can continue building this hierarchy and consider the order P equal to 3, which gives us 12 more vectorial base functions for HDiff and 5 more L2 scalar base functions. And so what's important here is that for each of the orders, the stability conditions, the inf subconditions, are satisfied for these two fields. So I will skip the functions which are similar to the already presented tutorials, and I will concentrate on the solving in the refinement loop. So here, before actually getting into the refinement loop, we solve the system once, and before solving, we need to assemble it, and this is what we will consider here. So assembly of the system starts from the functions similar to what was presented before for the Poisson problem. We need to calculate the Jacobian and inverse Jacobian. But here, what's specific for this problem is that we need to transform the base from H curl to HDiff. And we don't need to do anything by ourselves. We just need to push the operator to the pipeline. So I just want to remind you that all the computations are based on the operators, which are pushed to the pipelines, and then those pipelines are executed for each single finite element in the mesh. So here, using this operator, we ensure that the base will be computed correctly for each of the elements. And then to actually solve the system, we will not need to implement anything by ourselves. We will exploit the form integrators that Ignatius has just presented. For the diagonal term, we have this operator predefined, so as the operator for the off-diagonal symmetric terms. And finally, we just need to push the operator to compute the domain source for the known source function. And with that, we will assemble the system. And I will not stop on the solution because it's a linear problem and that is standard. What's more interesting is how do we check the error? So to check the error, we need to build the new pipeline and push the relevant operators. And basically, before actually computing the error in the operator that we will develop and implement, we need to pre-compute the values of the field U, its gradient, and values of the vectorial field flux at the Gauss points. There are also standard operators for that in MOFM. We don't need to work with those approximations. All what we need is to do the interesting part, the operator for the error. And basically what is happening in this operator, so just a reminder, this operator will be executed for every single quad in our mesh. Every quad element. And what we basically do here is we loop through the integration points, integrating the local error, knowing the analytical solution. And then we would also look into the semi-norm of the error. That's the norm of the difference between the gradient of the numerical solution and the analytical one. And finally, the interesting part, the local error indicator, computed based on the gradient of the computed field U and the numerical field flux. So those indicators are saved on the mesh on tags in a similar way to how Carol was presenting, and also they are summed up of the whole domain. If the user specifies a number of refinement iterations greater than 0, we would get into the loop of refinement, assemble the system, solution, checking the error, and repeating that. So I just want to be precise here that there could be different ways to refine in finite element method. We could consider the H refinement, which breaks the element into smaller ones, or the P refinement, which is increasing the order of approximation functions, or a certain combination of the two. So here, by the refining, we mean the P refinement. We will be increasing the order of the elements. So this is the basically pseudocode of the algorithm for this adaptive P refinement. It consists in 2 steps. First of all, we loop through all the domain entities, so the quad elements in this case, and we check the pre-computed value of the error indicator on each element. If this value is greater than the mean value of the whole domain, then this element should probably be refined. So it's added to the list of the elements to be refined. And when we check in this way all the elements, we loop from the list of elements which were marked to be refined, and we increase consistently their order by 1, such that in sub-conditions continue to be satisfied. And with this, we could start to do some convergent analysis, considering the first the global refinement. So at this step, we do not do any P refinement iterations. And we can check how, in this case, the error is decreasing with the decreasing element size for different polynomial orders. And what is clear here, we can immediately see how the using the higher orders is more effective than just doing the H refinement with the low polynomial orders. As, for example, those 2 simulations corresponding to the order 2 and order 4 have practically the same accuracy, but the one with the higher order is computed on the coarsest mesh, and the one with the low order is computed on the 10 times finer mesh. And the accuracy is the same. But in fact, this doesn't give us the whole picture. What we are interested in practical simulations is how the error is decreasing with the number of degrees of freedom needed for the computation. And again, if we locate the same simulations on these plots, we see that the green one over here, corresponding to the polynomial order 4, is requiring about 20 times less degrees of freedom than the blue one, corresponding to the to the polynomial order 2. However, what is going to happen if we're going to use our p-adaptive refinement? Where is going to be that curve? So before looking into that, we could just look into how the error indicator is actually working. So here I show for the previous step for one of the meshes, how does the error norm look like, computed as a L2 norm and or H1 semi-norm, and then the last one on the right is the error indicator. And we can see that the error indicator is very close to, so error indicator computed on the a posteriori on the values obtained after the solution is very close to the norm computed knowing the analytical solution. It's slightly lower, therefore it's not a strict mathematical bound, but it's sufficiently good to find the elements which have the highest error. And therefore we can run the adaptive p-refinement. So here we start with the order 2 everywhere in the domain, and we will see how the elements will have their order increased. And at the same time, how the error L2 norm will be decreasing the domain. So we start from the case where there's some elements with their error 10 to the power minus 6, and let's see how that is decreasing. So by the time we made a number of iterations of the p-refinement, yeah, let me stop at the last one over here, so we went to the approximation order 10 at some of the elements which had the highest error, and therefore the L2 norm dropped below to 10 to the power minus 24, which is quite effective. And so if we now plot this this curve for the adaptive p-refinement on our graph, so here this is again the evolution of the L2 norm with increasing the number of DOFs. We can see that we obtained the same accuracy with this p-refinement using now 50 times less degrees of freedom than the best one that we obtained by combining global H-refinement and global p-refinement. However, we could see that we had to make a significant number of iterations of the refinement there. So probably the algorithm that we implemented is a bit naive and has only like the testing purposes. And for real life application for something more complex, what would consider more sophisticated error indicators and maybe more sophisticated strategies for choosing the elements to refine. We have another tutorial, slightly more complex in MOFM, which is considering combination of H and P refinement for the problem, also for the same basic equation for the flow problem in a domain which has such a shape that it produces a singularity at a point. And in this case, the combination of the HP refinement driven by the error indicators provides almost exponential convergence. That's practically what I wanted to say about this. So I collected some of the possibly useful reading on the mixed finite elements and hierarchical approximation basis, especially the first book by both Brez and Fortan is a very useful one to learn how to work with the mixed finite elements. And also some literature on the a posteriori error estimates, which I used. And I would specifically mention the last one here is the work by my colleague Mebratu, who implemented a p-adaptive implicit-explicit mixed finite elements, which is now in the publication process. So in this talk, I discussed what is the motivation for unit mixed problems and how they can be obtained by introducing auxiliary variables. What are the a posteriori error estimates and how they rise in the mixed formulation, and how the mixed formulation can be implemented in a hierarchical and with a hierarchical and heterogeneous basis. And what we saw with this simple example, that global p-refinement is usually more effective than H-refinement. And also what we could see is that adaptive p-refinement permits to decrease significantly the number of degrees of freedom. So again, if you're interested, you could have a look into the corresponding tutorial on the MOFM web pages. Thank you.